In this video, we're going to cover section 4.4, which is exponential and logarithmic equations. We're going to solve exponential logarithmic equations and solve applied problems using exponential equations and use our logistic growth model. So, to recap just a little bit, if you have the same base and they have different powers, you can drop the bases and set them equal to each other and solve for the variable. Same with the logs, as long as the logs have the same base. You can drop the logs and set them equal to each other. And then inverse, if you take a to the log base a of x power, it equals x, and then opposite for logs. So we are going to rewrite these in any form that we can to make it work so it's easy to solve. This first one's pretty easy. And then, so 4 to the x equals, and then 64 is 4 cubed. So all I have to do is say x equals 3, because I can drop those 4's. And this one, so I have 10 to the x equals 300. Well, 300 to nothing, to 10 to any power doesn't get me to 300. So I need to rewrite this using this form right here. I'm going to rewrite it into log form. So I'm going to have log base 10, or you cannot write the 10 of 300 equals x. So then I don't know what this is, so I'm going to use my change of base formula that I talked about in 4.3. So I'm going to take log of 300 and divide by log of 10. And when you do that, it says to estimate to 3 decimal places, so that's 2.477. Equals x. So, and then e to the 4x equals 10. So e to the 4x, I don't really know. I can't write 10 as a power to the e to the power. So I'm going to take the inverse of those. So the inverse of e is natural log. So I'm going to take natural log of e to the 4x. And what I have to do to one side, I have to do to both sides. I'm going to take natural log of 10 as well. So then the ln of the natural log of e of 4x is just 4x, because the natural log and e cancel each other out. And then I have natural log of 10. And then I'm going to divide by 4. And once again, I'm going to round to 3 decimal places. So it's natural log of 10 divided by 4 is approximately 0.576. And you can always plug these back in and check them. Actually, I highly recommend that you do, because sometimes they won't always work. All right. Problem number 4, we need to isolate the exponential thing before we deal with anything. So I'm going to divide both sides by 2. So I have 4 to the x minus 2 equals 3. And once again, I can't rewrite 3 as a power of 4. So I'm going to rewrite this as logs. So log base 4 of 3 equals x minus 2. So then I'm going to, once again, I don't know what the log base 4 of 3 is. So I'm going to take log of 3 and divide it by log of 4 equals x minus 2. So whatever that log of 3, whatever this thing happens to be, I'll add 2 to that number. So x minus 2, and I'm going to round to 4 decimal places here, just so when I round to 3, well, we'll just round to 3, and then add 2, so you get 2.793 equals x. So those are some simple ones for solving exponential equations. And then we're going to solve logarithmic equations. We're also going to rewrite these in any form that works well for us. We might have to use our log rules or properties, and we might have to change it to exponential functions if it comes down to it. So I have log base 3 of x equals 2. So I am going to rewrite this one using our, where'd it go? This thing right here. So I'm going to have x equals 3 squared, and 3 squared is 9, so And then this one, I'm going to add 6 to both sides because I'm going to want to isolate my natural log. No, that's not 6 anymore. That's not 0 anymore. That's 6. And then I'm going to divide by 3, so natural log of x equals 2. But then I don't know what the natural log of x is, so I need to rewrite this into the e form. So x equals e squared, and then you just plug in e to your calculator, which is 7.39. I said 3 decimal places, but and I'm lenient on that. So this one, we cannot rewrite it. Well, we can. Yeah, we're going to. Sorry. So we're going to rewrite it into exponential form. So z minus 2 equals 2 cubed. Well, z minus 2 equals 8. Those 2's and z look too much alike. We'll zoom in. There we go. That looks a little better. Okay, so then you add 2 and z equals 10. And then this one, I'm going to use my properties. So since natural log of x is being added to natural log of x plus 2, I can write this as 1 natural log of x times x plus 2 equals x plus 6. Oops. Equals natural log. Sorry. I jumped the gun a little bit. So that means I can drop the natural logs. So I have x squared plus 2x equals x plus 6. So I'm going to move everything to one side, keeping my x squared positive. So x squared plus 2 plus x plus x minus 6 equals 0. So now you can use quadratic formula if you would like. However, I'm going to factor it. So what multiplies to negative 6 and adds to 1, 2 and 3. 3 is positive and 2 is negative. So x equals 2 and x equals negative 3. If you plug these back in, you'll notice that negative 3 doesn't work because you can't take the natural log of a negative number, or a log of a negative number for that matter. So 2 is your only solution. And then this one. So since this minus is here, that minus right there, we can rewrite this as log base 9 of x divided by x minus 1 equals a half. And then I'm going to rewrite this into exponential form. So x over x minus 1 equals 9 to the 1/2 power, and 9 to the 1/2 means the square root of 9. So x over x minus 1 equals 3. So now I can solve. So x now equals, I'm going to multiply x minus 1 on both sides. I'm going to distribute 3x minus 3, and then 0 equals 2x minus 3. So, and you get x equals 3/2 when you solve for x. And that does work. Next thing, applications. You're going to use continuous compounding of interest to determine doubling or tripling time. And we're going to use an exponential model to approximate these answers. This is the same continuous compounding formula we used earlier. But we want to find the time required for a $1,000 investment to double or to triple. We're going to do both double and triple at the interest rate of 12%. But we all know that we have to change it to a decimal. 0.12 per year, compounded continuously, and we're going to round to the nearest tenth of a year. So doubling time, that would be $2,000 equals 1,000 times e to the 0.12 t. We're going to divide by 1,000, so I'm going to get 2 equals e to the 0.12 t. And then what undoes e's is natural log, so I'm going to take the natural log of both sides. So I'm going to have, let's zoom in, natural log of 2 equals 0.12 t. Then I'm going to solve, so I'm going to divide by 0.12. So t is equal to, when you plug that in your calculator, you get 5.8 years when you round. So that's, if you double it, it would take 5.8 years, almost 6 years. And then tripling time. So tripling time would be $3,000 equals 1,000 e to the 0.12 t, because the rate's still the same. So 3 equals e to the 0.12 t. The steps are the same here. And then you take the natural log. It's just the numbers are different. So natural log of 3 over 0.12 is 9.6 years. Alright, those are how you do doubling and tripling. So the number of trees per acre, which we're going to call n, of a certain species, which who cares, is approximated by that lovely function there, with x between 5 and 40, and x is the average diameter in inches of the trees 3 feet above the ground, so 3 feet tall. And we're going to use the model to approximate to 2 decimal places the average diameter of it when n is 21. So we know that n is 21. So all that means is I'm going to plug in 21 for n. And then I'm going to write everything else. So there's my function. I'm going to divide by 68. So I have 21 over 68. I would not round at this point, because if you round at this point, you probably will get some of the decimal places off. So I'm just going to keep it as a fraction. And then how it log is base 10 and e is base e. So I can take the log of both sides, because it'll get rid of that 10. So log of 21 over 68 equals, helps if I write correctly, negative 0.04x. And then we're going to divide by negative 0.04. And then when you do that, you get x equals 12.76 inches. So that's the, when your tree is, when you have about 21 trees, your diameter is 12.6, a little bit more than a foot. So, last but not least, pretty sure. Yeah, not quite. We got this one on this page. Last one on this page. So we're going to use the formula to find this growth model here. So since we are given the y-intercept, we're going to use that first, because it's easy. So y is just going to stay as, well, y, this is x and this is y, so y is a half equals a to the e, b times 0. Well, that's 1/2 equals a e to the 0. E to the 0 is 1, so a, that thing just becomes 1. So a is a half. So since you know a is a half now, you are going to plug a back in, so y equals 1/2. Let's write it so you can actually read it. Y equals a half e to the bx. And then so we're going to use this next point, which is x and y. So we're going to say 5 equals 1/2 e to the b times 4. So then I'm going to divide by a half. So when you divide by half, you get 10 equals e to the 4b. And then this is just like we did before. We're going to take the natural log because it gets rid of our n. And then divide by 4. So b is approximately, it says 4 decimal places right there, so 0.5756. And then you plug it back in, so you have y equals 1/2 e to the 0.5756x. And this is the last one I would actually write now. Logistic growth model. So, using the data collected in an experiment, a biologist found the growth of a fruit fly, that's not hard for me to say at all, with a limited food supply could approximate, using that lovely function there, this great function, where t is the number of days since the start. So we want to first estimate after 10 days. So t is 10, so that means we want n of 10. So 400 over 1 plus 39. Once again, let's write it so you can read it. 400 over 1 plus 39, excuse me, e to the negative 0.16 times 10. Don't know why I put an extra parenthesis there. I just made it super long. And when you plug that in to your calculator, I would plug it in, I would do e to this. What I would do first is do e to this part first, and then multiply that by 39 and add 1, write that number down, and take that number and put 400 on top. And when you do that, you get 45 fruit flies. And then we want to figure out how many days the population be 100. So that was A, and this is B. Excuse me. So we want n of t to be 100, and then we're going to solve for t. So we're going to multiply both sides by the denominator, just to get it out of there. There's other ways you could do this, but to me this made the most sense. So those go away, and then I have 100 times, and I would not distribute the 100. You'll see why in just a second. So now I'm going to divide the 100. So I have 1 plus 39 e to the negative 0.16 t equals 4. Okay, and then I'm going to subtract 1. So I have 39 e to the negative 0.16 t equals 3. Now I'm going to divide by 39. So I have e to the negative 0.16 t equals 3 over 39. That is not a nice fraction. It's not ones we really know, so I'm not going to deal with that one. I was just going to leave it like that for now. And then natural log gets rid of my e. So I have negative 0.16 t equals natural log of 3 divided by 39. And then I'm going to divide by negative 0.16. So t equals, plug that all in, you get 16.03. So about 16 days.